Okay, so last time we got into chapter 1, which, as we talked about, is sort of like an introductory sort of chapter. As I mentioned before, there's a good amount of information about just basic math sort of operations, also some things about calculators and how to punch things into calculators, which is useful. I think we were talking about that towards the very end last time, and we'll come back and look at some of those things. I did just want to go back over a couple of the slides that we maybe skipped ahead with, and then we'll get back into some of the calculator stuff along the way. So very often in chemistry, things are given to you in terms of percentages. And a lot of times when we are given things in terms of percentages, we oftentimes want to use them as really conversion factors. So a lot of times it's very much easier to sort of take a percentage and sort of turn it into a regular number or a conversion factor that you could use in a calculation that you may be doing. So for example, if you had something that was, say, 5% by mass, which is what M/M means, mass to mass percent, sodium chloride. A lot of times when we do have some type of percentage that we want to kind of turn into, like I said, a kind of more usable sort of conversion factor or number, it's always good to assume 100 of it. And the reason we assume 100 is because the numbers stay the same. You could assume as much as you want, but the numbers would change, which makes it more complicated. So if we assume 100 of something, that allows us to kind of turn our percentage into a usable sort of number, a usable conversion factor. So for example, if something was 5% by mass sodium chloride, what that basically means is there would be, say, 5 grams of, put there. MM is mass to mass percent. So this is basically, and we'll learn it a little later on in a later chapter, but that's mass to mass percent. So basically kind of grams to grams of that. And really what it is, it's how many grams of what's dissolved in the solution to how many grams of the total solution there is. So when you make a solution, you take something that's a solid, typically, for example, you like sodium chloride, you dissolve it in some water and you then have like a solution of it. It all dissolves. And so the top part's really how many grams you took to kind of dissolve it to make the solution. The bottom part is really how many grams of the solution there is. So if we had something like this, what that would mean is we have 5 grams of sodium chloride really dissolved in 100 grams of solution. And this is really what is referred to as a conversion factor. And that is really a fraction where we could use it to convert between different things that we're looking for. Any type of conversion factor, by the way, as we will talk about more in the next chapter, you could use either way, right? In a fraction, basically, you have a numerator and a denominator. I think I got that right, top and bottom. And you could flip them around as well. So we could also say, for example, in 100 grams of this solution, there is 5 grams of sodium chloride. So these are actually two sort of conversion factors that we could get from a percentage that we could actually use, say, in a calculation. How would you do that? For example, obviously we'll do more examples of that, but let's just say that we wanted to know how many grams of sodium chloride there was in, say, 250 grams of a solution. So if we know that there is 250 grams of the solution, and we want to know how many grams of sodium chloride there would be in this type of solution, we want to get rid of the units of solution or grams of solution. So the idea here is, and what we're going to be looking at here is again, something we'll see more of when we get chapter 2 as well. But this is what is referred to as dimensional analysis in chemistry. And the way you want to show your work in chemistry is through what is known as dimensional analysis, which is what we want to do is pretty much get rid of the units we don't want, and we want to end up with the units we do want. So the way that you should look at this is when you do these type of problems, we oftentimes, when we do it, we use conversion factors like one of these two things. We might use this guy, we might use this guy. What determines which one that we want to use is, to keep it very simple, is opposites cancel. So if we want to get rid of a unit, we got to put the exact same unit in the opposite location. Now you may be looking at me and going, 250 grams of solution, what location is that? So although it is, wow, it's like possessed, I think. Wow. All right. Well, that was exciting. Let's just go back. No, maybe let's not go back. I don't know. All right. Hold on. All right. So when we look at this written like this, although it is not written as a fraction, it is essentially over 1, which means when we look at the units of grams of solution, which we want to get rid of, because we want to figure out how many grams of sodium chloride there is, the grams of solution is on top, right? Which means if we want to get rid of it, we need to put the exact same units on the bottom, which is the opposite location. When we look up here, would it be the one on the left or the one on the right that has grams of solution on the bottommost part? The one on the left, right? So that would be the actual conversion factor we would want to use in this case. And we would set it up like this. I like parentheses. Some people like lines, whatever you want to use. And we would go with 5 grams of sodium chloride on top and 100 grams of solution on the bottom. Now, what we're doing mathematically when we do dimensional analysis like this, and again, we're going to do a lot more examples in chapter 2, it's just kind of previewing a little bit here, is what we're doing mathematically is whatever is on top gets multiplied, and whatever's on the bottom gets divided. So what we would do here mathematically is we would multiply up on top 250 times 5 and hit equals, which would give us 1250. We then would come back and divide it by what's on the bottom, which is 100, and hit equals. And we end up with, over here, 12.5 grams of sodium chloride. So how do I get to those units? I get to those units because what happens here is the grams of solution on top and the grams of solution on the bottom will actually cancel each other out. So it's the same thing, for example, if I asked you, what is the answer if you took 2 divided by 2? That equals 1, right? They cancel each other out, basically. So if you have grams of solution on top and grams of solution on the bottom, equals 1, and they cancel each other out. So whenever you're doing something like dimensional analysis, which we do a lot in chemistry here, you always want to think opposites cancel. And you want to set up your work like I did there, where you could clearly see where the units are. So what happens, and we'll talk more about it when we get to chapter 2, is sometimes people don't really show their work nice and clean like that. And at some point when they go do the calculation, they're not really sure where the unit is. Should I be multiplying? Should I be dividing? And if you set it up like I just did there, and we'll talk about more again in the next chapter, there is no misunderstanding in terms of the math of what you need to do. Everything on top gets multiplied, everything on the bottom gets divided, and you just cancel out whatever units are on top and bottom. The unit that you're looking to end with is always should be on top, usually. If it's 1 unit, that unit needs to be up on top. Did you have a question, or? It's called dimensional analysis. Yeah. Yeah. And we're going to talk about it. It's official chapter 2. When we get there, we'll definitely talk about a lot more. But this is something that you want to really think about. And sometimes people are like, I don't really want to show my work that way. If you want all the credit, you need to show your work that way. But B, that we'll talk about when we do get to it next chapter as well, is there's formulas. And a lot of times, if you maybe do not know the formula that you need to use, you do know the unit that you end up with. You a lot of times could do calculations like dimensional analysis and just figure out, okay, I gotta get rid of that unit, keep this unit. Before you know it, will actually do for you in a lot of cases is it will do the formula for you without you having to worry about kind of. So you really do want to learn, besides the fact that that's how you show work in this class, but it can help you in that aspect of it, that you just get rid of sometimes some formulas and just go, okay, I got to end up with this unit. I'm starting with this unit. How do I get there with the information that's given to me? And you oftentimes can kind of get to the answer that you're looking for. So basically, in this case, we would have the sodium chloride, we would dissolve to make basically solution. But back to the original topic, side note there, I suppose, big side note, is percentages. So whenever you have a percentage, I would always recommend turning it into a conversion factor and really using it in sort of a dimensional analysis problem calculation. And really the best way to sort of use it. People overlook the percentage part of it and think they really don't have necessary any information give it to them. And if you do turn it into like a conversion factor, you'll see you have a lot of sort of information given to you. Obviously here, if we have 5% red balls, that means we basically have 5 red balls out of 100 total balls. And if we have 50% green, we got 50 green ones out of 100. So again, just assuming 100 with percentages is just the easy way to keep all the numbers the same. Numbers really change, and it's just an easier way to use it. Now, equations, we do have formulas obviously in this class, and part of the battle is to be able to rearrange formulas correctly and solve for whatever you're looking for. So again, basic sort of algebra and how things work when you have like an equal sign, which usually happens in any type of formula that you have, is to move something the other side of the equal sign. You always do basically the opposite operation of what it is. Again, it's opposites of a lot of what we do here. So if you ever have to move something to the other side, you basically do the opposite. So what do I mean by that? We want to obviously isolate the x in this case by ourselves. That means we need to move to the other side. Here it is plus, which we need to do the opposite, which is -8 from both sides, right? So we have it adding. So to do the opposite, we do subtracting it. Those guys go away. 2x equals, I can go with no calculator there, 6, and hope for the best. Now I need to solve for x by itself. So when I look at the x, 2x really means 2 times x, right? So it's basically multiplying. So to move the 2 to the other side, we do the opposite, which is dividing. So we got to divide to the other side. 2 gives us x is equal to 3, right? So when you're always moving across the equal sign to rearrange equation, you always basically do the opposite operation of what is there to solve for it. It also always, for example, though, if we have just a regular sort of formula like so, it always will end up in the opposite location if we're just rearranging to solve for it. So for example, if I want to solve for mass, volume's on the bottom. When it crosses the equal sign, it ends up on top, which means it will be volume times density is equal to the mass. If I want to solve for volume, I need to get volume to the other side on top, right? I cannot solve for volume on the right-hand side. If I solve for volume on the right-hand side, it is not volume, it is 1 over the volume, right? So it's the reciprocal. So whatever you're solving for, if it's just one thing by itself, doesn't need to be on top. So once again, opposite location, that goes to the top, which gives me d times v is equal to m. Now I need to solve for just v. They're multiplying here. Opposite means divide, right? So those guys divide. Volume will be mass divided by density. So it's always opposites in terms of dimensional analysis to get rid of units. You always put it in opposite locations if you want to cancel them. And things that are equal to each other in terms of formulas, when you go across the equal sign, they always end up in opposite locations. What we're really doing here is multiplying the volume to both sides, the opposite product here. And then obviously we're dividing the density to the other side, in this case, opposite of multiplying. Any questions on that? So rearranging equation is really important. We do hit a lot of equations along the way, and definitely when we get to, say, the gas chapter, we do hit a lot of equations that you do need to rearrange. So for example, here, if I want to solve, let's say I want to solve for V2, what would V2 equal? Why don't you give it a go and see what you end up with? Why don't you also, for this one, what would T1 equal? Rearrange it and solve for T1. Okay, so let's take a look. So once again, a couple ways you could do it. You could just do the quick way and just move things to the opposite locations, or you could do the mathematical way, which is basically the same thing. So here we want to basically isolate V2, which is over here. We are multiplying there. So again, opposite to move it to the other side means we need to divide the P2 to both sides. Those guys cancel, gives us V2 equals P1, V1, P2. Question on that there. Now, if you want to do maybe a quicker way, you can, think of this as, again, a fraction, which means I need to move that to the opposite location, which is on the bottom there, right? It was on top to begin with and gives you the same thing as in the middle there. So again, opposite location is where things end up when they go across the equal sign. Here for T1, you want to do the quick move. We need to first get this guy to the top, right? Since we're solving for it, it's on the bottom, so we can't have it on the bottom if we're solving for it. So I could do the quick way, which is I know it's on the bottom there. When it goes across, it will end up on top, right? And that will give me V1 is equal to V2 T1 T2. I now need to leave this guy there and move everybody else to the other side, right? So quickly doing that, V2 is on top, which means it should end up on the bottom. T2 is on the bottom, it should end up on top. And basically we'll end up with V1 T2, V2 is equal to T1. So again, just moving everybody to opposite locations. Mathematically, what we're really doing here is multiplying and dividing. So the first thing that we did is multiply T1 to both sides. Those guys canceled, gave us V1, V2, T1, T2. Next, we multiplied T2 to both sides. Those guys canceled, gives us T2, V1, V2, T1. Lastly, we divided V2 to both sides. Those guys cancel, gets us there. Yeah. So that is basically what we are doing here. The quick way is just to go opposites, right? Just move it to the opposite location. Think of everything like a fraction, top and bottom. It's if on the top, it will end up on the bottom if you move it. It's on the bottom, it'll end up on top as you go across the equal sign. And that's just sort of the quick way to do it. Now you can see here, sometimes here, there's a lot of formulas you might have to rearrange. And this is again where sometimes dimensional analysis can help you out by just looking at units and again, sort of canceling these things out. Any questions on rearranging equations? If that is something you struggle with, you should practice again, just rearranging the equations as we go through them in the different chapters to make sure that you know how to properly sort of solve for whatever you're looking to solve for. Yes, sir. Say it one more time. I'm sorry. Right here. What we just did. It's really just rearranging an equation to solve for a variable. So it's kind of like x, how we had x in the very first one. We were trying to solve for x. In any type of sort of chemistry formula that you get, there's usually one variable that you want to solve for. So V and T in this case all stands for volume and temperature. So in this case, we're looking for like the second the first temperature, and we have like the second temperature and the two volumes given to us. So usually in these situations, for example, like something like that, you would have 3 of the 4 given to you, right? And you just want to make sure that you know how to rearrange it correctly. It is very common that people misrearrange the equations and then you get the wrong answer when you plop the numbers in the wrong spots, right? So it's important to be able to sort of rearrange those things as we go through the chapter so that you can kind of put those things in the correct spots and things cancel out. That's also why units are really important, because if you do the wrong math, but you do have the correct units everywhere, you hopefully should see at the end, like, oh, wait, I'm solving for like a temperature, but I got like volume units still left over, so that can't be right. So this is why it's also really important in your calculations that you keep units when you're doing the calculations, because even if you maybe screwed up the math part of it, hopefully you could recognize by just looking at the units, wait, that's not what I should end up with. If I'm looking for a temperature, I should end up with something that's like a temperature unit, like Kelvin, degrees Celsius, something like that. But I ended up with like milliliters, which is a volume. So that's never not going to be a good job rearranging that. All right, so we did that. We pretty much not going to look too much at graphs in here. We did start talking about scientific notation. I think we talked about using our calculators. And again, remember that you do have exponent buttons. You do have, again, an EE button. You do have an EXP button probably on your calculator. And again, probably the other one is something like this, and along with that will. So as we talked about, this is definitely the buttons that you want to use when you write a number in scientific notation. Remember that a number in scientific notation, n times 10 to the n, where this is a number between 1 and 10, again, not 10 or above, not less than 1, so it's got to at least be 1, less than 10. And this, again, is a number that you move either right or left the decimal place to get it to a number between 1 and 10. So again, if we have 325 and we want to turn that into scientific notation, one place gives us 32.5, which is not a number between 1 and 10. One more place there is 3.25, which is a number between 1 and 10, times 10 to the 2. Typically, larger numbers will have positive exponents, or if you move the decimal point to the left, it will give you a positive exponent. If you have something like 0.044, here we go one place, two places to get to a number between 1 and 4. 1 and 10, which is 4.4 times 10. This is going to be negative 2. 2 is how many places we need to move, but this is going to be negative because it is a small number and we move the decimal place to the right. Right, we talked about scientific notation at the end last time, right? I think, yeah. So more importantly, I think as we finished up on last time, is understanding how to punch these into your calculator. And the other important buttons is your negative button, which usually looks like this or this. Once again, it is not your subtract button, so you want to make sure that you do use the correct button. So if we were going to put this guy into our calculator, as we talked about, 3.25, we would hit our exponent button. That again will probably give you a 3.25 and an E, or maybe a 3.25, pop up some zeros. And remember that this button here stands for the times 10 part. So you don't hit the multiplication button as we talked about last time. You don't do any weird buttons. You just hit the exponent button. What's left is our exponent, which is a 2. That's a 2. And that will then turn that into a 2. And again, that is the proper way to punch it into your calculator. Again, if you have a negative exponent, it works pretty much the same way. You would go 4.4. Once again, hit your exponent button. Going to go 4.4 with the E, or 4.4 times 10 to the couple of zeros. Now we're going to hit our negative button here. I'll put a negative, I'll put a negative, and in this case a 2. We'll put a 2 and put a 2. And again, this is definitely the way that you want to punch these numbers into your calculator using scientific notation. You do not want to use the shift log button. You don't want to use the multiplication button unless you're multiplying numbers. But to actually punch the one individual number in scientific notation in your calculation, you do not want to use any multiplication button. think we also talked about this combination. Really, in most cases, if you have this combination, in a lot of cases, it's kind of like a two-tone sort of calculator. The only difference is, as I mentioned before, you do have to kind of put parentheses around each number that you put in scientific notation. You got to make sure that your parentheses are big parentheses on both sides, not like a little one on top. Got to be big on both sides to do that. But it's basically punched in the same way. Any questions on that there? Probably where most people go incorrect is trying to punch it in. So why don't we try a couple, maybe, why don't you try these two and see what answers you get? We're going to take 6.2 times 10 to the minus 11. We're going to divide it by 3.7 times 10 to the 22. And then we'll take 4.15 times 10 to the 6 and times it by 7.7 to the minus 12, looks like. Yeah. Okay, so let's take a look. And again, if we're going to punch the first one in here, this is what you should really punch in. You should go with 6.2. You then should hit your exponent button, which once again will take care of this part of the number. It is a negative exponent here, so a negative button and an 11. Then you hit your divide button and punch the other guy in the same way, 3.7. Once again, exponent button, and that looks like a positive 22. And you hit equals. Yeah. Now on your display, you might have something that looks like, all right, what's on mine? 1.675675668 minus 33. So that is what my calculator basically spit out to me on my screen. Now, a couple important things about this, and also something that people do very, very commonly when they have a number that's given to them as an answer in scientific notation in terms of their calculator is they actually forget to actually give the proper number. We'll talk in the next chapter why we were going to round, but we're going to round it to 1.7, and there is a reason, and we'll talk about it in the next chapter. But the thing that people oftentimes forget is found way on the right of your display, right about there. And on some people's calculators, it may actually be like times 10 to the minus 33, or it may even have on some people's calculators like a little space, and then it'll go like minus 33 next to it, depending on your display. So if you look to the right of your answer on your calculator, that is the rest of the number. The answer here is not 1.7. It's actually, remember that the E stands for the times 10 part. So that is times 10 to the minus 33 would be the correct answer in this case. So you want to make sure you don't forget the sort of exponent part of the answer. And that is a really, really common error that people make. They see the front numbers and they forget about, oh, it's like actually times 10 to the something on the back side of it. So make sure that you don't forget that back part of it. Also, when you are writing an answer that's in scientific notation, that is how you should do it, as times 10 to the minus 33. You shouldn't write it 1.7 E minus 33. So the E is just used for really calculators and Excel and computer type programs. But when you're writing an answer in scientific notation, you should write it as times 10 to the whatever the exponent part is. Any questions on that? Yeah. Mhm. Yeah, so it depends on your calculator, and that's actually your I call it your negative button. And usually on most people's calculators, the negative button, which is really the one that changes the sign of the number on your calculator, I call it a negative button. It will either look like that, like a plus slash minus type button, or some calculators will have like a parentheses and a minus in it. It is not the subtract button though, so don't use the subtract button for that part of it. So you got to find kind of the button on your calculator, and those are probably the two most common sort of change the sign buttons to actually change the sign. Yeah. You wrote it out manually, like you did like you did like 6 2 0 0 0, a bunch of zeros. Is that what we're talking about? I would say, so I'm not sure exactly how you're punching it in, but I would say that you should use this button for exponents. Now, if you're using like the inverse lot now, so if you look on your calculator under around where the log button is, there's a 10 to the x or something like that. If you're using that button, is that the one you're talking about? Yeah. Th that yeah. So if you're using like this, that's incorrect. You will get the wrong answer. That's the inverse log, and you don't want to use that. You'll get lucky sometimes, but if you start incorporating things like logs with it, you'll be way off and stuff like that. So you definitely don't want to use that. You also typically don't want to do it like, 6.2, hit the multiplication button. Sometimes there's like a 10 and a caret type button as well. You really don't want to be using that type of button. You will get lucky in certain cases, and a lot of cases you won't be so lucky and stuff like that. So that's why most calculators will have a dedicated button that's supposed to be used whenever you do scientific notation. So you always want to do that. And what will happen is it won't be necessarily a lot of times you're like way off, but what you'll usually notice if you like punched it in incorrectly is like this part of the number is all good, but this part's just off by like one or something like that. And that's really because you're not using the correct button. And because even though it doesn't seem like it's going to do like a slightly different math, it will do a slightly different math. Yeah. Yep. Other questions? Okay, so let's take a look at the next one, and we want to punch it in the same way. Obviously, if you have the one where you need to do parentheses, you got to parentheses up, each of these numbers on your calculator. If you have that one, obviously, that you need to do the parentheses. Now, for the next one, we want to go 4.15. Once again, we're going to do our exponent button. And in this case, we do have a positive 6, so we're going to go 6. We're going to hit the multiplication button in this case, and 7.7 exponent button. Once again, we have a negative 22, I think it says. So we're going to do our negative button to turn it into a negative number, 22, and then hit equals. So is that 22 or 12? That's 12, isn't it? No, it's kind of like a 22 if you looked at it wrong. We'll go with 12. All right, so when you do that with the 12, not the 22, you will get on your display 0.000031955. Once again, this is what you'll see on your display in most cases. Now, just so you know, your calculator will not give you necessarily the answer always in scientific notation unless you tell it to do so. Most people don't tell it to do so. So sometimes it will do so and give it your answer in scientific notation because it just runs out of room. So it's got to do it. Or if you program it to always give it to you in scientific notation, then every number will be given to you in scientific notation. In this case here, again, we'll talk in the next chapter why we round, but we would end up with something like 0.00032 in this case. Also, a couple of things, when you do write a small number like this in a decimal, you should always include the 0 before the decimal point. It keeps the numbers from running together, and that way there's clear delineation between each numbers. So make sure that you do include that as well. Any questions on either of those or how to punch in scientific notation? Once again, if you're still not sure where your button is, or it doesn't seem like you know how to use it, just at some point bring it down. I'll be happy to try to find it with you. There are some obviously variables, but this is probably the 3 most common buttons that you would use for scientific notation. Any questions on that? Yeah. Yes, it would. It would actually be 30. Yeah, the 32 at the end of it. Yeah. No, if you wanted to, we could give the answer in scientific notation, which means we could go 1, 2, 3, 4, 5, and that would give us something like 3.2 times 10 to the minus 5. Either one's perfectly fine. Yeah, so you could give it in scientific notation if you wanted to, or in this case, you can leave it in decimal place. So I might have mentioned it last time, so I'm going to just re-mention it one more time. For me personally, you do not need to give every answer in scientific notation. Unless obviously the instructions say to do so. I will say, as we talked about in the next chapter, you are supposed to give your answers to the correct number of significant figures. And sometimes the only way to get the correct number of significant figures is to write it in scientific notation. So there's sometimes no way to put a number just in decimal form, if you will, in the correct number of significant figures without doing scientific notation. The reason for that is I might have mentioned it last time, but if not, let me just mention it now. When you write a number in scientific notation, for example, n times 10 to the n, all the numbers that come before the times 10 part of a number written in scientific notation, they're what are considered significant figures. And we're going to talk obviously more about that in the next chapter as well, but they're considered significant figures. But since your book puts scientific notation in chapter 1, where it should usually be with chapter 2, we'll talk a little bit about it now. So what I mean by that is, for example, let's just say we did a calculation and we got on our answer like 12,000, right? And we want to give this answer to 3 significant figures. The way that 12,000 is written right now, there is actually only 2 significant figures. There is no way to get it to 3 significant figures without writing it in scientific notation. Now, if I take this and put this into scientific notation, 1, 2, 3, and 4, I could write 1.20 times 10 to the 4. It now has 3 numbers before the times 10 part, and those 3 would be significant figures. So now it does have 3 significant figures. It still represents 12,000, and that would be the only way you could do 12,000 with 3 significant figures. Now, let's just say that I wanted 4 significant figures. Not a problem either, because I could write 1.200 times 10 to the 4. There's now 4 numbers before the times 10 part, which means now it has 4 significant figures. So the advantage of scientific notation is that, like I said, in some cases, to give an answer to correct number of significant figures, the only way to do that is with scientific notation. And the nice thing about it is you could actually control how many significant figures you want. If I wanted 1 significant figure, I could just write 1 times 10 to the 4, and now I have 1 significant figure. So scientific notation is a technique that sometimes you will use because really there's no other way to get to the right number of significant figures. And most importantly, what scientific notation is for is what we originally talked about. It helps you with really large numbers and really small numbers, so you don't have all those zeros and stuff, and they get lost along the way in calculations. Any questions on that there? All right, so I think that is chapter 1. And again, they also have in your book here some examples, as we've been talking about, in terms of calculators and how to punch it in. I think that's chapter 1. I think that's good. Next. Okay, so we're off to chapter 2, which is measurements. So in this chapter, we're definitely going to talk about significant figures. We're going to talk about how to take proper measurements. We're going to talk about some of the other stuff that we sort of touched upon in chapter 1. We're going to talk about dimensional analysis, how to solve problems, conversion factors, and then we will finish up with a talk of density at the end. So let's get going on it, I guess. All right, so let's talk a little bit about measurements, and more importantly, let's talk about units and the importance of units. So for example, if I just say I have 100, once again, who knows what I'm talking about? 100 by itself really gives you no information. Again, it could be you have $100, you can have 100 pennies, you could have 100 bananas, whatever it may be. But really, without the unit part of the measurement's pretty much worthless because nobody knows what that unit is or that number is really referring to. So whenever you take a measurement, there should always be numbers and there should always be units involved. And without both of those things, like I mentioned before, it's kind of useless. The actual number value of it. So we obviously have lots of different units there. As you can see in this picture, we have degrees Fahrenheit, which is a temperature. We have pounds, which is a mass. We have inches, which is a length. We also have miles and kilometers, which is a length as well. So we have many different units, and they do represent different types of sort of measurements, different types of quantities. And it's really important as well to understand, what those units do represent. So when you say something like, I got 5 grams, you're talking about a mass and not like a volume or something like that. So that's really important. So how many different types of units do we have? Well, for the most part, there's two types of systems. There's what is commonly referred to as the English system of units, which is what we use here in the US. And then pretty much everybody else in the world uses the metric system. So as you can imagine, it probably is not a great thing as everybody is doing business and working with people and all kinds of outposts here in the world. That if some people are using English units, some people are using metric units, there's going to be some type of mistake that's going to happen when I start talking about English units and somebody else is talking metric. Like when you look in your car, right, on your speedometer, if you have maybe an older one that actually has like a needle, some of the newer ones you can set to it. But there used to be miles per hour, which is what we use, right? But there's also kilometers per hour, right? Which is metric, which is what everybody else sort of uses. I think on your digital ones, you could display it as kilometers per hour as well. So in 1960, they actually had a convention on units, which sounds like fun, not really. But what came out of that was this idea of what is referred to as the SI units. The SI units is the International System of Units. It is basically, for all intents purposes, the metric system. And it is what is usually used in chemistry, and it's used, in science. So sometimes you'll see things like the SI unit is this or the SI unit is that. And that's sort of the basic sort of official system of measurements that's used around the world for things like length, volume, mass, temperature, and time. And speaking of that, when we talk about volume, the SI unit is the cubic meter. The metric is the liter. When we talk about length, the SI unit is a meter. When we talk about mass, the SI unit is a kilogram. When we talk about temperature, which might be a unit you're not familiar with, but will definitely be by the time we're done with this class, that is Kelvin, and that is a unit of temperature that pretty much 99.99% of everything uses Kelvin in terms of formulas in chemistry. You always got to convert things to Kelvin when you're using a chemical formula. Time is seconds. So this again is what I was talking about a second ago. It's really important that when you write a unit or see a unit, you understand what that is actually measuring. So if you say centimeters or meters or kilometers, you're talking about some type of unit of length, as opposed to a volume, which is like liters, milliliters, cubic centimeters, which is a volume, or something like kilograms, grams, milligrams, that is masses. I can't tell you how many people have come up to me over the years and I ask something like, what was the mass of your beaker? And they go 52.55 milliliters, which is a volume, not a mass. Yeah. So, these are things that you want to make sure that you understand, what the unit represents in terms of the type of measurement that you're taking. So let's talk a little bit about that. Volume is the space that is occupied by some type of substance. It is measured in cubic meters. Common units of volume is liters and milliliters. Common conversion, 1,000 milliliters equals 1 liter. So that is a conversion you use a lot in chemistry. Also, 1 milliliter equals 1 cubic centimeter, which is also 1 cc, in case you're giving somebody a shot, right? Give that guy 5 cc's of this before they die. That is like a milliliter, basically, along the way. So a cubic centimeter is a volume. So if you have something like a cube, one way you could actually get the volume of an object that is like a solid object, let's say a cube, is you could take the length times the width times the height. And each of these are length measurements. So you take centimeters times centimeters times centimeters. So each of these individual measurements are lengths. But when you multiply them together and you get a cubic centimeter and you cube it, That is a volume. So cubic centimeter is a volume. Cubic decimeter is a volume. Meters cubed is a volume. So that is a very common way that we sometimes will deal with the volume of, say, a solid object like a cube. You could get that. By the way, when we look at something like a graduated cylinder, which is here, which is a good piece of equipment to measure out a certain amount of a liquid, we typically will see when you put a liquid in a glass sort of container, like a graduated cylinder, like a test tube, like anything that's glass, basically a beaker, you typically will see the curvature of the liquid. That is what is known as the meniscus. And we typically always read from the bottom of the meniscus. And the reason for that is this. What is happening in this case is the attractive force between the liquid and the glass is stronger than the attractive force between the liquid and itself. So what happens on the sides through capillary action is the liquid that touches the glass starts to rise because the attraction is stronger. And what happens is we get the rising of the liquid on the sides that are in contact with the glass container. The middle part that's not in contact with the glass container stays put. And the reason we take the reading from the bottom of the meniscus is without that attractive force, it wouldn't go up the sides and the actual volume would be what it looks like in the middle. And that's why we read from the bottom of the meniscus in most cases. Not all meniscus are this sort of U-shaped meniscus. There are few substances where actually the attractive force between the substance and itself is stronger than the substance and the glass. Very common example, which you probably won't see because they've taken mercury out of most labs, is mercury actually will have a kind of reverse meniscus where it will actually go upward. And in that case, you would actually read from the top of the meniscus because, again, that attraction to itself makes it come in on itself and come down. And the true level is actually up at where the middle part is. So I would say probably 99 times out of 100, that is what your meniscus is going to look like, a U. Sometimes it's a lot easier to see. Sometimes it's not very easy to see depending on your glassware. If you put some solution in something that has a really big diameter glassware, that meniscus is going to get really spread out. You're not going to be able to really see it really well. If you have something like a graduated cylinder, which is a little smaller diameter, you'll be able to probably see it a lot better. So you should always try to read a liquid and the volume that you have from the bottom of the meniscus. And again, those are some very common sort of conversions that we use a lot in chemistry. Again, that 1 liter is 1,000 milliliters. Say this guy pops up occasionally. 946 milliliters is 1 quart, but definitely that 1,000 milliliters is a liter. The reason we use the sort of liters to milliliters conversion a lot is the very common way that we sort of collect a volume, say in the laboratory, is we oftentimes will collect it in milliliters. Problem with that is a lot of chemistry type of formulas require the volume to be in liters. So we oftentimes will collect the actual number in milliliters and it has to convert it to liters to use it in a calculation or something like that. So going between liters to milliliters and milliliters to liters is a very common sort of back and forth. The good news about a milliliter and a cubic centimeter is it's a 1-to-1 relationship, which means you just change the units, the number stays the same. Length is measured again in units of meters is very common. Centimeters is also very common. Millimeters is also very common. So when we look at a ruler, for example, just a normal basic ruler. Up on top, we have these numbers, right? And these are inches, right? On the bottom, we also have some numbers, which are centimeters on the bottom of a typical ruler. Then we have little numbers. These little numbers are, those little dashes are millimeters. Yeah, there's 10 millimeters in a centimeter. So if we look at a ruler, up on top are inches, on the bottom typically are centimeters. The little dashes on the bottom where the centimeters are millimeters when we look at. Those are three very common units. One relationship is, as we will see, 1 inch is equal to 2.54 centimeters exactly. That's an exact sort of conversion. And that's also going between the English unit of measurements or units and the metric unit. So that is the relationship between an inch and a centimeter. And if you look at a ruler, if you come down, I obviously didn't draw it very good, but that would be like 2.54 centimeters coming down at the 1 inch mark. So a couple of common conversions. 1 meter is 100 centimeters. We use a lot. A meter is 39.4 inches, 2.54 centimeters in an inch. Also, 1 kilometer is 1,000 meters. That's also one that we use a lot as well. Mass is the amount of quantity of matter there is in an object. We measure the mass a lot of times on a equipment like you see in this picture. That's a digital balance. A balance is a fancy word for a scale, and that's what we call it in the lab. Oftentimes kilograms, but most of the time, if you're going to use a balance like this, that's probably going to be in grams. By the way, if you have a digital sort of balance or really anything that is digital and it gives you a number, it's important to record all the numbers. They're important, otherwise they wouldn't be on the digital display. So when you're recording things that are digital, like in the lab, and it has numbers, unless otherwise instructed to only record so many digits, you typically should record all the numbers that are there on your paper. There is a difference between mass, for example, and weight. Weight takes into account the force of gravity. Mass is sort of independent of the force of gravity. So our weight here and our weight on the moon will be different because the gravitational force is different, about 1/6 or whatever it is here. And our mass, though, will be the same in both cases. So although the process of when we go sort of get the mass of an object is the process known as weighing, in chemistry and typically science, you should refer to it as the mass of the object and not the weight of the object. So you should refer to it as getting the mass of the object rather than the weight of the object when you get it. Any questions on that there? Continue on. So we've been talking about mass here, and again, very common units of mass are definitely these. Like I said, grams is pretty much in the laboratory, for example, always the units you're going to probably sort of measure, but we very commonly will need to convert it to kilograms, or we have kilograms to grams. So that definitely is a conversion that's used a lot. Also, pounds to grams is also used a good amount. Sometimes people will use 453.6 grams equals 1 pound. I almost want to say that there might be a mastering chemistry problem where they actually use the 453.6 rather than 454, and they might mark it wrong because of that, because it's a little slightly different. So just keep that in mind. And if you use 454 and you feel like you did the calculation correctly, try with 453.6. And although it doesn't seem like it might make a big difference, sometimes it will. Let's talk a little about temperature, and there really is sort of 3 temperature scales that we deal with in chemistry. There is degrees Fahrenheit, there is degrees Celsius, and there is Kelvin. And degrees Fahrenheit is like the temperature scale we use for like our temperature and the temperature outside, which is like 200 degrees in the last couple of days. Although this building feels good when you walk in, that's pretty good. Degrees Celsius is also very commonly used. By the way, water boils at 100 degrees Celsius, which is a good thing to know. That's the normal boiling point of water. Water freezes at 0 degrees Celsius, also the good thing to know. So where water freezes, which is the freezing point, 0 degrees Celsius, 100 degrees Celsius is boiling point. Those are two numbers that also are pop up along the way. Kelvin is the unit of temperature that we use the most in chemistry. One major difference about it is not degrees Kelvin. So we do not use the degree symbol, that little circle. We do not use that little circle like we do here. So there is no circle. It is just called Kelvin. So if you have something like 373 Kelvin, that is how you would report it. We'll talk about it, even though it might be a later chapter. But to convert between these, which is really the conversion we do the most, a lot of times we do need the temperature in Kelvin. Once again, more so for calculations. Pretty much all chemistry calculations, if you're doing any type of calculation that involves temperature, pretty much it needs to be in Kelvin to go into the formulas. So to convert Celsius into Kelvin, we add 273 to it. So you take the temperature in Celsius, add 273. The actual real number is 273.15. Most people don't use the 0.15 because it gets rounded off a lot of times anyways. So I'm good with 273. But if you do see 273.15, that really is the true conversion factor that you use. That also means that if you have the temperature in Kelvin and want Celsius, you take the temperature in Kelvin minus 273. So I would say probably 99 times out of 100, what you will be doing is taking the temperature from Celsius and converting it into Kelvin. And it is, as we'll talk about when we get to those sort of formulas, even if you are given the temperature in Celsius and you're asked to give the answer in degrees Celsius, when you go into the chemistry formula or chemical formula, you do actually convert it to Kelvin and then convert it to Celsius after you get the answer. So we oftentimes do have to do that conversion. To calculate our Fahrenheit, temperature in Fahrenheit is equal to 1.8 temperature in Celsius plus a 32. By the way, 1.8 is maybe if you learned a fraction, 9 divided by 5, same deal. It is basically 1.8. And lastly, if we need to convert to Celsius from Fahrenheit, temperature in Fahrenheit minus 32 divided by 1.8. So those are the formulas to convert temperature from one unit to the next. Out of all of these, and probably after chapter 2, you probably won't see degrees Fahrenheit all that much. It's going to be pretty much Celsius, and probably doing this conversion here, converting Celsius into Kelvin is probably most of the time what you're going to do. Probably the second most of the time what you'll do after that is this one, taking Kelvin back to Kelvin back to Celsius is the two most common ones. Now, when we do a conversion like this of temperature, we'll use this page here. So let's just say that we had 32.5 degrees Celsius, and we want to know, how much Kelvin that is, or what is the value in Kelvin. So we would take our formula, which is the temperature in Kelvin is equal to the temperature in Celsius plus 273. We'll go 32.5 plus 273 equals, on our calculator, 305. Jeez. 305.5 Kelvin in this case. Now, how far should you take your answer? There is kind of a special rule that we follow specifically for just temperature to temperature conversions. So if you are simply just converting this temperature value from, say, Celsius to Kelvin, Kelvin to Celsius, Celsius to Fahrenheit, whatever it may be, all you're doing is basically just converting the units of it from one temperature unit to the next. We always make our answer look like the original number. So what that means is, if we look at the example we just did, our original number went to 1 decimal place. So when we convert it, we take it to 1 decimal place. Now, if our original number was a whole number, we would take the answer to a whole number if we're just strictly doing temperature to temperature conversions. So why don't you try one? Let's just say we had, let's say we're 98.6 degrees Fahrenheit and you wanted degrees Celsius. So take a moment and convert that. Take a look. So in this case, we want to go from Fahrenheit to Celsius. So the temperature in Celsius is equal to the temperature in Fahrenheit minus 32 divided by 1.8. So putting in our number there, 98.6 minus 32 divided by 1.8. Remember that we do the top part first and subtract 98.6 minus 32. By the way, hit equals. Don't punch it all in at once. Yeah. Then we're going to divide by the bottom 1.8. That is going to give us on our calculator 37 degrees Celsius. Should that be the right answer in this case? The answer is no, because our original number went to how many decimal places? 1, which means when we convert this guy, we really should call this 37.0 degrees Celsius and take it to 1 decimal place. So again, if you're just simply doing temperature to temperature conversions, all you're doing is just changing the units. Always make the converted number look like the original number. If we were doing like 98, then we could have left it at 37 when we converted it. Any questions on those there? All right. Truthfully, it might be chapter 3. Yes. You do in this particular case because of the original number that was given to us. So the original temperature number that we were converting went to 1 decimal place. So when we converted, in this particular case, I just made up the number there and we actually hit a whole number. Because we actually do need to take it to 1 decimal place, we do have to add the 0 here in that 1 decimal place to make it be just like it was when it started. Otherwise, we kind of lose sort of some significant figures in that case. So this rule that we're talking about here is going to be a little bit different than other rules we talk about. This rule of make it look like the original number is specific to only temperature to temperature conversion. So if you're just converting the temperature, that is the general rule of how you should end your answer or get your number. Other questions? All right, so got that. Time is obviously seconds. I guess we'll talk about it, I suppose. How many seconds are in a minute? 60 seconds in a minute. That's good. How many minutes in an hour? 60 minutes in an hour. How many hours in a day? Yeah, not 60, right? All right, 24 hours in a day. People roll 60 hours in a day. Nobody wants that. So make sure you know that. 24 might be too many. So just a reminder, some things may not be given to you. So, I hope you know something like that. That probably won't be provided for you. Also left and right, may not as well. I do understand that things happen. So you could come ask, I felt bad one time somebody, on stress of the test or something. They were like, they came up and they stood facing me and they're like left and right. And I'm like, your left or my left? Because you're now facing me, we're backward. So, sometimes stuff happens. And again, some of the stuff might not be provided for you. If you forget, you could come ask. I might tell you, I suppose, or help you figure it out, I suppose. All right. So as I mentioned before, it's really important to know what the unit really does represent. So if we look at this, if I got 2.6 kilograms is a mass, right? 1.7 meters is a length, right? We got 0.5 grams is a mass, right? Liters is a volume. So again, recognizing what those units represent in terms of the type of measurement is really, really important as well. I think we did all right on that one. That's good. All right. So again, we saw in that table our SI units. Again, cubic meter for volume, kilogram, meter, and Kelvin there for our temperature. All right, so take a moment here and answer these. Identify the measurement that is in the SI unit for each of these. So take a moment for each of them and see which one is our SI unit. Meters seems like an SI unit there for length. We have the mass of a lemon, ounces, kilograms, pounds, kilograms, yep. And temperature, Kelvin, right? Sounds good to me. Any questions on those there? Okay. There we go. All right, so let's get into it now. We're going to talk now really about measured numbers and significant figures. And really, we're going to kind of might bounce around a little bit here, but since it all is going to be kind of related to each other, how to take a measurement, how to count significant figures, that's basically what we're going to talk about now, which is probably the lab you're going to do next week, I think, is the opening lab there, I think. So there's really two types of numbers that we come across in chemistry. There are what are referred to as measured numbers. And measured numbers is pretty much what the title sounds like. They come from some type of measurement that you actually take. You maybe put something on a balance and get the mass of it. You take a ruler, get the length of it. You take some type of measurement, basically. They are what are referred to as being quantitative. Quantitative means you took some type of measurement, is basically what that means. The other type of number that we come across is what is referred to as an exact number. And there really is sort of two ways that we see exact numbers sort of in chemistry. One way is it is something that is just counted. The other way is it's some type of definition, like 1 inch now. Well, I will go with 12 inches equals 1 foot. There are 12 inches in 1 foot. So that's what's known as an equality. And that basically is what's considered a definition, or what we saw earlier, 1 inch is 2.54 centimeters. That's also an exact number. Counted is pretty much this. If I had these two cups or whatever here on the desk, I'm not going to do some type of experiment to figure out how many cups I have. I'm simply just going to count it, right? I'm going to count what's there. The classic textbook example, maybe a couple of baseballs, but the classic textbook example is like you have a bucket of apples, basically, right? You're just going to count how many apples you have, like in the bucket along the way. So we're going to focus in on first measured numbers and taking measurements and how to properly take measurements. So let's talk about that. So let's say we have a ruler like this. And we'll go centimeters. And let's just say we got like an arrow that we want to measure. All right. So whenever you take a measurement, no matter what type of measurement that you take, there is always going to be some degree of uncertainty associated with it, some degree of guessing, basically, when you take a measurement, which sounds kind of funny. You're taking a measurement, so you're not guessing. But built into the measurement that you're taking is a degree of uncertainty, and it's actually based on the equipment that you're using to take that measurement. So depending on the piece of equipment that you use to take the measurement, the degree of uncertainty changes depending on how many markings there are, how less markings there are. But typically speaking, when you take a measurement, you always want to look at the markings on the piece of equipment that you're using. There's really two types of markings. There is a large marking and what I call small markings. So for example, the large markings typically have numbers, as we see here. and that is 1 centimeter and 2 centimeters. The difference between 1 and 2 is 1 centimeter, right? So the biggest markings, the distance between the two biggest markings represent 1 centimeter. The other thing that you want to figure out is, what does the smaller markings represent? The smaller markings represent a certain amount, in this case of length. So you need to figure out how many small markings there are between the two big markings. And there really is an important place of where you should start counting. So you should always start counting the smaller markings that don't have like numbers on them. You should always start counting after the last one that does have a number. So after the last large marking is where you should start counting. So that's 1, that's 2, that's 3, that's 4, that's 5, 6, 7, 8, 9, and you should end at the next big marking. So here we're going to start at the marking after the 1, and we're going to count up all the small markings until we hit the next big number, which is a 2. I think I said 10, right? That each of the small markings represents how much? It is 0.1 centimeters. By the way, you could get that by simply dividing the large marking by 10 small markings, right? Gives you 0.1, yeah? So that means that this marking right here is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then obviously we go to 2 next to it. Any questions on that so far? Okay. So when you take a measurement, there should always be numbers that no matter who looks at it, everybody should agree. And those are what are referred to as being certain numbers. Everybody should be certain. So if we look at my arrow, everybody should be certain it is at least 1.4, right? So it definitely crosses past the 1.4 marking there. So we would record that 1.4. This is considered all the certain numbers. The problem is my arrow doesn't stop at 1.4, right? It goes past it. It doesn't actually hit the 1.5 marking either, right? So it stops before the 1.5. This is where the uncertainty comes into play. I may look at it and go, well, I think my guy ends about halfway between those two markings. So halfway between something is like 5, right? Between 10, right? So halfway is 5. And I may record a 5 along with my units. And this is what is referred to as the first uncertain number. Now, why it's uncertain is somebody else may look at it and go, I think it's a little further than halfway. So maybe it's like a 6 or a 7, or maybe if I drew my arrow really close to the 1.5, maybe it's like an 8 or a 9. So the idea here is it's kind of like plus or minus that uncertain digit at the end. So what we're saying when we record this is, I think it's about 1.45. But maybe it's like 1.46, maybe it's 1.44, it's somewhere in that ballpark. And if you look at where it's sitting, that's pretty accurate as to sort of where the end of it is. It's somewhere in that ballpark. So when we do this, and when you take a measurement, you should always record all the certain numbers plus the first uncertain number in your measurement along with the units. When you do that and you record all the certain numbers plus the first uncertain number, that is what we like to call in the business here significant figures, which means my measurement I just took has how many significant figures? Has 3 significant figures. The uncertain digit again is the 5, right? Any questions on that there? So what's also important is you should look at the different pieces of glassware or measurements that you make, because scales are different. So for example, if we look at, say, a graduated cylinder, which is professionally badly drawn right here in front of you, there we go. We have our 10, 20, we'll do some milliliters. We'll put some beverage in there, maybe a little blue Kool-Aid or something. There we go. Our meniscus kind of going on there. So again, we want to do the same thing as what we did before. We want to look at the large markings, right? Now, in this particular case, we have a 10 here and we have a 20. The difference between 10 and 20 is 10 milliliters, right? 20 minus 10 is 10, right? We again want to figure out how many of those small markings we have between the big markings. So we again are going to start counting past the 10 because that's the last large marking that we had. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 small markings. That means each small marking represents how much? So big marking is 10 milliliters, and there's 10 markings between it. 10 divided by 10 is 1 milliliter. Yeah. There's 10 small markings, right? Gives us basically 1 milliliter each of those. That means that this marking is 11, that is 12, that is 13, that is 14, 15, 16, 17, 18, 19, and 20 as we go up there. Any questions on that there? So again, we want to take a proper reading. So we go from our bottom of our meniscus. Our certain number is definitely 15, right? It's at least 15. So we want to record that. Now we do have that estimation. Once again, it kind of looked like maybe I'll go lower, a little short than half. We'll go with that for here. So maybe I call it a 4 milliliters, right? All my certain numbers. My first uncertain number. That means that this measurement here, how many significant figures? It does have 3 significant figures in this case as well. Question on that there. Now, again, it does depend on the scaling you look at, which is why you should always look at it, because even in the laboratory, the person next to you may pull out from their drawer a graduated cylinder, and you may pull out from your drawer the same size graduated cylinder, like a 10 milliliter, but they might have been made by different people and they might have different scales on them. So you should always look at the scale that you have. Hopefully not. Hopefully they bought them all from the same, but when they start breaking, they got to replace them. They buy it from whoever's cheap. So they might not have the same scale. So if we look at one here, again, I'm going to draw another graduated cylinder. It's hard to believe I failed art 3 times. I know it is. That's all right, so we got that. We're gonna pop in our drink here. We'll do a little green drink, whatever that green drink might be, I suppose. All right, you take the reading. Give the proper. We want to figure out our large markings. So once again, we got a 10 and a 20. So we do know our large markings here is actually again 10 milliliters. We do want to figure out our small. And again, we're going to do our sort of counting starting after the 10 in this case and stopping at the next big marking. So we got 1, 2, 3, 4, and 5 in this case. That means in this particular case, each of the small markings represents how much? It does represent 2 milliliters. Again, you could divide that by 5 and you got 2 milliliters, right? So when we look at this, this is actually 12, 14, 16, 18. Like I'm doing a 2, 4, 6, 8, who we appreciate type of thing going on here. So if we look at our level there, we're between 16 and 18. What becomes, or what comes between 16 and 18? Yeah, it is 17 in this case, yeah. That means that this particular number would have how many significant figures? Would have only 2 significant figures. Which one would be the uncertain number? It would be the 7 is our uncertain number, right? The best you could do on this particular scale is actually take it to the first number there, the ones place, right? And that is because when we look at the difference between 16 to 18, there's not enough room in that little space to figure out where 16 stops and where 17 begins. So there's not enough room to figure that out. We could do that on like this one because it's just like one digit difference. So like halfway there, you're halfway to the next number. But here, there's too many number differences between those markings. There's no way to do that in that particular case. Question on that there. You would do at 17. We would not put 17.0 because then it would have how many significant figures? Yeah, and that's not what we could do on this particular scale. We could not go out that far. So typically speaking, you could usually go to one more place to the right of the smallest marking. So if you could figure out what the smallest marking represents, you should take your reading typically one more place to the right. The exception would be this one, right? We can't go one more place to the right in this particular case. So not in all cases. So there is also another way if you want to sort of figure out how far you should take a reading, which is if you could figure out what these smallest markings represent, you could actually just divide it by 2 and it'll tell you how far you should take the reading. For example, I can figure out that my smallest marking is 2. If I divide that by 2, that is 1 milliliter. That should go to a whole number. If I look at the previous ones we did, the smallest marking here is 1. If I divide it by 2, that's 0.5 milliliters. That's the first decimal place. That's how far I should take the reading to. If I look at the original one, smallest marking was 0.1 divided by 2, 0.05 centimeters, 2 decimal places. That's how far you can take the reading to. So in general, you could go one more place to the right of the smallest marking. If you're very confident of what the smallest marking represents in terms of its value, you could just simply divide it by 2, and whatever the 5 part of it is not important, but however many decimal places that number ends up is how many you should take your reading to, one more place to the right. Question on how to take a proper reading there. Let's say we had the same ruler that we started with on the first one. And let's just say that we end up right on this line. And we know already that our large marking is 1 centimeter. As we saw, our small marking is 0.1 centimeters. Again, this being 1.1, 1.2, 1.3, 1.4, 1.5, 1.7, 1.8, 1.9, and 2. So definitely it's on 1.3. So I record 1.3 centimeters. I record 1.30 centimeters. I record 1.3000 just to be safe. 0.000 centimeters. Too many, by the way. It just feels like too many. It's just too many. Yes. Is there a difference? Does it matter which one you record since it's right on the line? The answer is probably yes. I already asked that question, I imagine. So let's just start with significant figures, right? The first number, if I recorded this number here on the left, how many significant figures would it have? It would have 2 significant figures. The uncertain number would be which number? It would be the 3, right? So if we recorded 1.3 centimeters like that, what we're really saying is, I think it's 1.3 centimeters. It could be 1.4 centimeters, right? Plus or minus 1 of the uncertain digit. Or it could be like as low as 1.2. And if we look at where it is in the actual picture, it's really nowhere near either of those numbers, right? So that is a big amount of error, right? That's a big amount of, I'm not really sure where it's at, which unfortunately on this particular ruler, you could actually do better. So you would not want to do that, right? If we look at 1.30, it has how many significant figures? It does have 3. The uncertain number is, it is the 0, right? That's the uncertain number. So when we record that, we're saying it's 1.30 centimeters. Could be 1.31, could be like 1.29, as the uncertainty there's in that last digit, for example. And that is pretty much what we see, right? A lot less uncertainty. So you would want to record 1.30 centimeters in this case, because the equipment that you're using has the ability to take the reading out to the second decimal place. If you loft off a zero and you loft off a significant figure, you frankly just made your calculation pretty crappy. Yes, there's a lot more error involved in it that you should not have based on the piece of equipment that you use. Typically, when you take measurements, you want to use equipment that gives you less error, right? Less kind of like I'm sort of guessing the best I can do, right? So if you have the ability to take it to a certain number of digits based on the scaling, you sometimes do need to add a zero to maintain it not being less significant figures than it really should. So that happens a lot. People see it right on the line and they're like, it's just like, I'm just going to record that because there's like a number on that line and I can read the number and I know it's at least that. So I'm just going to record that. It always amazes me in lab every time, people go to the balance and they weigh out exactly the number you need, which is very highly unlikely, just so you know. It's very hard to do, unless you sit there a very long time to try to weigh out the exact number that you're supposed to measure out. So make sure, again, on the digital one, you record all the numbers. It's really important to look at the scaling like we're talking about here, taking measurements so that you take it to the right number of digits, and you don't want to shortchange your measurement by lofting off some numbers when you have the ability to take it out to a further sort of reading. The further you take this reading, the much better measurement it is than it was, for example, with 1.3. 1.3, we have the uncertainty in the tenths place, right? 1.30, we have it in the hundredth place, right? So we can go further out. It's a much better measurement, and we have the ability to do that. Any questions on how to take measurements? So now that we've talked a little bit about how to take proper measurements, let's talk about some of these examples here, perhaps. For example, if we look at this particular one here, that is 4, that is 5. So our large markings here is 1 centimeter. By the way, our small marking is, in this case, 1 centimeter as well, right? It's the same markings, right? So we could take this to 4.5 centimeters, one more place to the right of the smallest marking, right? Also, if you take 1 centimeter, which is the smallest marking, divided by 2, you get 0.5 centimeters, 1 decimal place. That is where you should take it, yes? That has how many significant figures? 2. Uncertain number is the 5. By the way, as we'll talk about shortly, the uncertain number estimated digit is not always the last number written. It is definitely the last significant figure that is written. So that's not always the same thing. A lot of times it is the last number that you see, but it's not always going to be the last number that's written, but it will be the last significant figure written. Here, as you can see, 4.5, they agree, that's good. Here we again got a ruler like we were looking at. We got 4 and 5, which are large markings, is 1 centimeter. If you count them up, we have 10 little markings going on between the two. So again, 1 divided by 10 gives you how much the small markings represents, which is our 0.1 centimeter. We could then go one more place to the right typically, and that is how we get to our 4.55, as it right here is 4.5. And that is our certain numbers, and our first uncertain number. This again would have 3 significant figures in this particular measurement. Any questions on those there? All right, there's our 3. So why don't you give the measurement on that one as best as you can. There we go. We'll go there. That is a 9 below it. I think the scaling got a little messed up on PowerPoint, but so that is 9 right there. This big line is 9. That's 8. And this guy's 10. So how long is that red line? So it is definitely at least 9, right? The large markings here are between 9 and 10 is 1 centimeter, right? Again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings, right? Which means if we take our small markings, that is 1 divided by 10, 0.1 centimeters, right? Which means we should be able to, if it's dead on that 9.2 right there, because we could go one more place to the right, this should be 9.20 in this case, which has how many significant figures? 3. Uncertain number is 0. Yeah. So this is an example where we hit right on the line, but because of the scaling on this particular equipment, we have the ability to go out one more place, and we do have to add the 0 in this case. This is just like the example we were just talking about. If we went 9.2, it should only have 2 significant figures. Uncertain number would be the 2, and it's a much worse calculation or measurement, which it shouldn't be. Any questions on that there? All right, there we go. So let's talk about how we count significant figures and what really does classify as a significant figure. First off, the rules for significant figures are as follows. All non-zeros numbers are significant figures. So if I have 1, 2, 4, 5, how many significant figures does that have? It would have 4 significant figures. By the way, we always start counting left to right, and we always start counting once we find the very first non-zero. So you go left to right. You do not start counting your significant figures until you hit the very first non-zero number, and then you keep counting. Now let's talk about the zeros, which is what gives people trouble. There are actually 3 types of zeros. So type 1 of zeros is what's called a leading zero. It is not significant. So if you had a number like 0.000124, how many significant figures does it have? It does have 3. Again, starting left to right, we do not start counting until we hit the 1, right? And now the rest of them are non-zeros. So the 1, the 2, and the 4, this guy would have 3 significant figures, which are those guys right there. Yeah. Better ones are sort of placeholders, right? To give it sort of value. The next type of zero is a trapped zero, or a captive zero, sometimes called. Those are significant. Those are zeros that are between 2 non-zero numbers. So those are zeros that are between 2 non-zero numbers. So if I have 40007, how many significant figures does it have? It does have 5. We start counting here. That's our first non-zero. These zeros are trapped between 2 non-zero numbers. That makes them significant. So that is 4. And one more here at the end is 5. Question on that there. Last one, which is the one that gives people the hardest time, that's sometimes referred to as a trailing zero. And they are significant if there is a decimal point in the number. Now, the decimal point does not need to be near the 0. It just needs to be anywhere in the number, and it will make those zeros at the end significant. So for example, if I had, we'll do 400 like this. So let's call this 400 centimeters, right? How many significant figures is that? The answer is it has 1. These zeros are at the end. They're trailing zeros. Is there a decimal point written? They are not significant then. So this would be 1 significant figure. Only the 4 in the front there. That means that what you're saying in that case is this a great measurement? You're saying, I think it's 400, but could be 500 or 300. That's a pretty big room for error there, right? So it's not a great measurement and stuff like that. Now, if I do this, how many significant figures is that? Now it will have 3. We have those zeros at the end, and this is where we start counting. These are significant because of the decimal point that's written. This would be 3 significant figures. Much better, because now we're saying I think it's 400, but could be 399 or 401, right? The uncertain number, by the way, in the bottom one is which number is the uncertain number? It is the last 0 is the uncertain number here. Yeah. Where is the uncertain number in the first one? On top there, the 400 with no decimal point. The uncertain number is this one. And this is what I was talking about earlier. That is not the last number written, right? But that is the last significant figure that is written. So that was what I was saying earlier, that the uncertain number is not always necessarily the last number that's written. Again, a lot of times it is, but it definitely should always be the last significant figure that's in your number. Hence back to something like 12,000. How many significant figures? 2, right? Starting here, that's significant, that's significant. These are not significant because there's no decimal. The uncertain number is which number? It is the 2, yeah? And that is where the uncertainty lies, right? And that's what makes up significant figures. Might be a post-lab question or a lab question, that particular one, by the way. Question on how to count significant figures. Just for fun, if I had this number 0.000300042560000 centimeters. I'm not sure how you measure that, by the way. How many significant figures is that? I don't know either. Let me count. I hear 8. Any other numbers? How many? 11. Any other numbers? All right, let's see. Let's analyze it here. All right, we're gonna start here. Not significant, right? Are these zeros significant? They're not, because we are not starting to count until we hit this guy, right? That's our very first non-zero. Now we have some zeros that are trapped. Are they significant? They are. So I'm just gonna put some checks there. That's check, that's check, check. That's a 4, so that's definitely significant. That's a 2, that's significant. That's significant, that's significant because it's non-zero. Now we have zeros at the end. Are the zeros at the end significant? That is both answers. One of them could be right. There is a decimal point in this number, right? So does that make those zeros significant or not significant? It is. There is a decimal point in here. Even though it's way over here, there's still a decimal point in this number, which will then turn these guys into being significant. It's a lot of check marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 looks like a winner in that case. Any questions on that there? Yeah. If it didn't have a decimal, you probably wouldn't have the zeros in front, obviously, so you would have probably something like this. How many significant figures did that one have? I heard 7 and 8. I didn't hear 11 again, which is good, I suppose, right? Since I took off some zeros. All right, started counting here. That's significant, yes. Still significant. Still significant, 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 significant. Zeros at the end, are they significant? No, no more decimal point, right? So now we got 1, 2, 3, 4, 5, 6, 7 in that particular case. Any questions on that there? All right, well, I'm gonna stop there. I need a nap.